Hi everyone, welcome to the Gillian-While demo. Today we will showcase the direct application of separation logic and CSE that you have learned throughout the past few days. Let's take a look at the simple example you saw in the Gillian taster. Here is the list predicate and the recursive list length function that you are all too familiar with. However, there are some key differences. First of all, there is this derived bounds heap assertion that is a combination of heap assertion star the bound assertion, making sure that actually x points to a binary cell. Also, notice how in the predicate signature that x has a plus right next to it, while alpha doesn't. To ensure the decidability, Gillian requires predicates to differentiate between in variables, x in this case, and out variables, alpha, where the out variables can be deduced without existential quantifiers from if you actually know the in variables. In this situation, if you know the memory location of the linked list, you can actually deduce the contents by traversing it. Now, what is actually different from this function? Well, in the Gillian taster, you saw Gillian in semi-automatic mode. Now, what does this mean? In Gillian, a predicate and its definition aren't immediately considered equivalent, but you can, through logical commands, freely unfold a predicate into its definition and fold the relevant pieces into the predicate. Gillian is able to automatically insert these logical commands most of the time, but sometimes it needs a little bit more help from the user. Now, for the sake of presentation, let's turn that off and see what happens. Now, Gillian is in what we call manual mode, and you can immediately see that the function no longer verifies. Let's try to figure out why by pressing the verify list ln button. So now that we have the debugger up, let's try to go through the true case and see if that holds. Oh, you can see that in this time, even the empty case does not hold. Let's try to figure out why. Here in the match node, you can see that red equals len alpha does not hold. Now, why is that? I mean, I would think that it should hold. If you press this node right here and look to the left to see your program store, we do know that red is equal to 0. That's exactly what we want. But do we actually know if the length of alpha? Well, if we open our predicate and our pure formulae, we can see that we have absolutely no information about alpha. Alpha is hidden in this list predicate here. So what do? Well, we can unfold the list and now you can see that if we start the debugging again, we can see that it still fails, however, for an entirely different reason. Now it actually does hold because we do have information about alpha, but we've lost information about the predicate list. So what can we do? Well, let's actually try to fold the list back up. And now you can see through our LSP that there is no squiggly line at the end, meaning that we actually have verified the function. Now we can assume that it is going to be the same reasoning for the non-empty case. And you can see that it holds. Now in Gillian, again, like I said, you almost never ever have to put these statements because Gillian is clever enough to figure out when it actually needs to unfold and fold the list. However, there are some cases that this might not be as trivial. One key thing to note is about the assert statement. So if we look at the false case, and when we unfold the list, we get new information, and specifically we get new information about our existential variables. These existential variables are, if given a fresh name, and you can see this by opening your peer formulae and see that now you have LVAR2 and LVAR0, LVAR3. These are auto-generated names and don't really help while we're actually trying to debug this program. This is where the assert statement comes in. So this logical command, all it really does is actually check if this logical assertion actually holds with the state that we have. Though it has an added bonus that whatever we put in this bind statement right here actually gets named as the existentials that appear in this logical assertion. So if we rerun the program, you can see that now the names are actually well named, and we don't actually have any LVARs. So great, now we've successfully verified this function. Now let's look at a more real-world example that we have gotten from the collection C library and adapted it to be in Whistle. You will later see this in C as well, where we try to verify it. All right. So you may have seen already this example through the exercises, but to reiterate, we have a singly linked list where we really want to make it more efficient to append something at the end. Additionally, we also want to not have to call list length every time that we want to know the size of a list. So we actually store these two new information by having this list predicate, this really big list predicate that is formed by these two smaller list predicates that we already know. This list predicate here is the same one that we've always worked with, and this is the same one, list segment, that we have worked with before. Now, CCListHT has two cases. One case that we can treat as the empty case, where X points to size 0, and head and tail, where head is null and tail is null. We also have the case where X, the list is actually not empty, and X points to the size of the list and head and tail, and there is a list segment from head to tail, and tail has one more non-empty pointer to the last element. Additionally, the size also, as you can see here, is the size of the list segment plus 1 to account for that last element. Now, lastly, we have this predicate CCList, which just calls the inner predicate and extensionally quantifies the head and the tail, since we don't really need to work with them when we want to do any verification with this predicate. Now, we have two lemmas to work with, one that you may have seen before in the Gillian taster, and one that is new, which just says that if you have a list segment from X to Y and another list segment from Y to Z, well, you can combine these two list segments to be one, and the mathematical is just the concatenation. A note about lemmas, you're actually able to prove them through putting a series of logical commands, and if you apply the lemma that you want to prove, you can think about it as applying the inductive hypothesis. Now let's actually try to verify the function CC_list_concat. Now this is actually a simpler version of what you would see with the other list predicate, because we don't actually need while loops in this case. Now, as you can see, it fails at the end. You can see that it says couldn't satisfy post condition. Let's see why that is by pressing verify CC_list_concat. Now, immediately you can see that since we're in auto mode, Gillian tries to unfold the first list predicate right from the get-go because it needs to know information about the size of the list. So if we press one in this case means that we're working with the empty case. You can see here that now we have to work with y as well, the non-empty and empty case. So let's try to see for the case when both of them are empty. Well, intuitively we can see that this won't actually ever be a problem because it is very easy to just fold the list back up and it will just all work out. And that is the case. It is the same case for when y is non-empty. And we can say the same thing for when y is actually empty, but x isn't. So the real interesting case would be when both of them are non-empty. So let's use the assert statements again, just to actually make it nicer to read. So, and now we've actually gone to the bulk of the program. We can see that in this program, intuitively, it is actually trying to, first of all, grab information about the tail of x, which is this statement here, the head of y, and the tail of y. And if we go down to these last three, this one is trying to connect the pointer to the next pointer of the tail of x to the head of y. While, I skipped one. While this one is trying to say that the new tail of x is actually the tail of y. And you can kind of see how that actually connects everything together with the predicates that we have. And lastly, we're trying to say that the actual size is just the sum of both lists. Now, if we open up our, go look at the left and open up our predicates and pure formulae, we can see that we have a bunch of information, but the information that we really should look out for is the list segments. Because if we want to prove that the resulting post condition, we need one really big list segment connecting from the head of x to the tail of y. So you can see here we have list segment head of x to tail of y. That's put in this funny notation, but if you actually look down here, it actually means the tail of x. We also have the list segment from head of y to tail of y. Now, how do we actually connect these two together? Well, we can't connect it exactly yet because remember, the tail of x actually connects to the head of y. We have that singular heap assertion that we need to connect first. So we need to actually apply else-seg append first. And then, well, now that we have actually connected the head of x to the head of y, we should have a list segment from head of x to head of y. But now we have that really nice connection, head of x to head of y and head of y to tail of y with the list segments. So we can actually apply the list segment concat here as well. And now you can see that the function already verifies, and we didn't even need to put any fold and unfold. We just needed to apply some lemmas. Now, just to see that it actually is working all completely, let's go down here to verify our intuition. You can see here again, before we apply the lemmas, we have head of x, head of tail of x, head of y to tail of y. If we step 1, we have head of x, head of y, with the concatenation of the lists, and we have head of y, tail of y. And then at the end, we have one big list segment, head of x to tail of y, with their concatenation of this ginormous list. And yeah, now we have verified 2 completely different functions with 2 different list predicates. Hopefully this gives you a good idea of how Gillian and CSE works, and feel free to try it out yourself.